All right, so this is where we left off last time. So for anyone who wasn't here on Wednesday because they were snowed in or something, hopefully you watched the YouTube video. In fact, were there any questions about like last time's lecture? All right. Did I hit record? Yeah. So we were talking about the growth function and how we go from the growth function to like our asymptotic complexity. How we don't really care about the full detail of the growth function because something like n squared plus 15n plus 7, it's going to grow like n squared. The other stuff is like almost inconsequential. It is inconsequential. So that's how we go from t of n to our big O notation. But how on earth do we actually get a t of n? Well, you just look at the code, and it might be simpler than you expect. It's just, you just look at the code. And after I show you all of like the correct ways to do it, I'm going to show you the tricks to kind of quickly figure out what t of n is. And often, you don't even need to know what t of n is to just go straight to the big O. This is when you're doing it like quick and dirty. If we were doing this with full rigor, if this was next semester, yeah, you're going to go more detail. But for our purposes, what I'm going to show you is going to be sufficient. So whenever you have like a statement like x equals 0, y equals 1, z equals x plus y, each of those things might take a different amount of work total, like the actual amount of work the CPU has to do those things. The point is, each of those things takes constant time. Doing 3 things that takes constant time takes constant time. All right? So something like that, it's order 1. Even though you're like, well, it's 3. Yeah, but it's constant. And we represent constant with just a 1. So we would say big O, 1. That means constant time. And the reason it's constant is the amount of work it needs to do doesn't change relative to any input size. I could say, here's the code. Oh, and you have an array of size 1,000,000. And you go, okay, but it's still only 3 lines of code that do 3, it's constant time. There's nothing to it. So any questions about that example? Now, whenever you're doing this, you always like just add together the total amount of work, and then like you simplify. So 1 unit of work, 1 unit of work, 1 unit of work added together, that's 3. That's constant time. So whenever we have like a simple statement like that, that's what we're looking for. So t of n is 3, but it's order 1. Now again, I'm going to say that's probably not the most accurate t of n. It's sufficient for our needs because again, the total amount of work each of those statements might be a little different, but it's fine for us right now. Now, look at this code. And the trick is, like, first of all, like, don't try to skip any steps. How much work is happening? Well, outside of the loop, there is 1 unit of work. And inside the loop, there's 1 unit of work. However, how many times will that inside loop run? N. So if you are doing 1 unit of work n times, how much work are you doing? N. So this would be like the 1 plus the 1 times n. All right? Any questions? Sometimes people feel like this is a bit of a logical jump. Yeah?
So the 4 on line 2 and the 3, line 3, that's one statement?
Yeah, but that statement, think about what that statement really means to the computer. It means repeat this n times. So we really don't care about the overhead associated with like the setup of the for loop. It's just part of the for loop. Let's say that the setup for it is constant time. What really matters is this line 3 is going to be run n times. So the total t of n is going to be 1 plus 1 times n. And whenever you see something like that, well, we don't care about constants. We don't care about coefficients. This is just big O of n. It's linear. Here's the first quick and dirty rule. Whenever you see a loop a single old loop, and the loop runs from like 0 to n, where n is some arbitrary like input, it's going to be linear. Almost always. Not always, but very, 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 very often, it's just going to be linear. I'll show you some exceptions. Now, if I had code like this, but n would only ever be like, I know that n is going to be like no more than 100. Anyone know what I would call this work? Like what the big O of that would be? If I know n is like, oh, I've got some fixed length array, the array is always like 100, so like how much work is that going to be? 100, which is, it's constant. So just because there is a loop doesn't mean it's linear. It's like, if we have to think about like how many times is that loop running relative to some input size. And here we're assuming some value n is some arbitrary changeable value. But if n is kind of like fixed, it's going to be constant. Hell, n could be 1,000,000. And if n's always 1,000,000, it's constant time. Because n isn't really changing. So it's not that it's a loop. It's that it's a loop that's the amount of time the loop is going to run is something that can be changed. Is that clear? Like who here's on assignment, working on assignment 2? Like you could have a loop to check the 4 directions, like up, down, left, right. Sure, you've got a loop, but that loop's only ever going to run 4 times, meaning it's constant time. Now the actual maze solving, that's a little different. That depends on the actual size of the maze. The bigger the size of the maze, the total amount of work, it's going to be bigger. And it's often important, we'll get this later. It's often important to be very aware of what the input size is. If I told you you always have a square maze, right? And you have a total of 100 cells in your maze. What would your knee-jerk reaction be for like your maze solver? What's the computational complexity of your maze solver in that case? You know what? I think I'm jumping ahead too far. We'll get to these ideas a little later in the semester. Don't worry about it. I threw you from the deep end to the deeper end, so don't worry about it. For me, I've always kind of visualized, like, okay, this loop. How many times is this loop going to run? Well, if I've got like a number line, I would put my finger on each of these things. Like the loop has to run for each of these values of I, all the way up to n, right? So how many things did I put my finger on? N. That's kind of how I visualize it. Yeah. Now, when we have nested loops, it might feel as if this is getting weird, but, well, first let's calculate T of n. All right? Well, there's 2 units of work on the outside of all the loops. But line 4, how many times is line 4 going to get run? Just someone very confidently say it. N times. There you go. Why? Well, because there's a loop that goes from 0 to n, and line 4 will run that many times. But here's the question I have for you. How many times will line 6 actually run? N times. Because think about it this way. Ignore the outside. Only look at the loop with the j in it. Right? So when you look at line 6, ignore everything else except lines 5, 6, and 7 right now. How many times will line 6 run? N. Once for each of the loop for j from 0 to n minus 1. Right? So line 6 will run n times, but
for every I increment.
Exactly. But then the question is, how many times is lines, like how many times does that inside for loop actually run? Well, that whole for loop has to get run n times. And that whole for loop does n units of work. So if I have to do n units of work n times, that's like n squared, right? Let's just add all these things up. All right? So here we have 1n squared. We could do this whole calculation, right? This part right here is the 1n, okay? Plus the one more unit of work, that's this whole bit right here. And that whole bit is being run how many times? N times, because of that outside loop. Plus 2 because of these two lines of code, which if we multiply that out, we get n squared plus n plus 2. Any questions about that? Did I go too fast? Did I jump anything? So in this particular situation, the order is, well, I only care about the dominant term, and I don't care about any coefficients. Well, there is no coefficient in front of the n squared, the dominant term. It grows n squared. Like, it grows like n squared. It's a quadratic growth function. Any questions? I can't tell. You all, the looks on all your faces are very, like, indifferent. So I can never tell. Give me more, like, active feedback with your faces. All right, you're happy. I'm moving on. So this just explains it. But, you know, if I visualize that one loop, like a number line, well, I have to do that whole number line n times. And if I do that, I end up generating this like this square, right? And I've got two values in each of them. Pretend one's I and the other one's j. When I is 0, we have to have j of 0, 1, 2, 3, all the way to n minus 1. We increment I, start j over at 0. And so it turns into this grid, literally a square. We have to do n things n times. Yeah, you're all so blank-faced right now. I can't tell. So here's my big, okay, pause. So I told you, usually whenever you see a regular loop and you've got a loop to some n where n is some variable value, it's going to be linear. It's going to be order n. Whenever you see nested loops, you usually think, your brain usually goes to n squared. That's usually your first assumption. Okay, you see nested loops, assume it's n squared until proven otherwise. Now the reason these are multiplied is because they're nested. If I had two loops, one after the other, but they're entirely independent, but they both run to n, that would be n units of work plus n units of work. Well, that's 2n. I don't care about the coefficient, it's still linear. But what's this one? Look at the code carefully. Just give everyone a chance. Give everyone a chance. If it's not immediately obvious to you, that's fine, you're normal. But let me pose it this way. Just really, how many times will this loop run? Yeah, half of n. Because I'm not counting by 1, I'm counting by 2. So I go, if I'm going towards n and I count by 1 every time, if I'm taking one step to n every time, it's going to take me n steps to get there. But if I have these steps, but I'm actually like skipping one every time, I'm counting by 2s, I'll miss half of the values. I go from 0 to 2. I skipped 1. I'll skip 3. I'll skip 5, and so on. I'm always counting by 2s. So it's going to be half of n. But 1/2 times n, well, 1/2 is just a coefficient. So although you say, look, if I had those two loops, one after the other, that was 2n. But it's still linear. And you would say, well, but one is more work than the other. You're right, but you're missing the point. The point is, the total amount of work that code's going to do scales linearly relative to the input size. This is just the same idea, but the other way. One's doing n units of work, the other one's doing half of that, but they're both linear. If I double the input size, I'm going to be doing like twice as much work. Oh, here's a good one. Okay, before I move on to that one, are there any questions about this one? Like, go back to this number line. If I start at 0 and I'm counting by 2s, I go from 0 to 2 to 4 to 6 and so on and so on and so on. I'm skipping half of the values. So that's why I'm doing, that loop's actually going to run half of the total amount of time. So now this one I'm going to give you a few seconds to think about. Pay special attention to the code and tell me how much work is this actually doing. And you know what? Don't even worry about T of n now. Just try to go straight to what the big O is. By the way, we've seen this pattern several times in like 161 and 162 already, but you just haven't really noticed it. This might be the first time we're kind of like putting it on display. Now, I'm not going to ask anybody yet, but raise your hand if you've got an answer in your head. You're like, I've got an answer locked in. Really high, I want to see. Okay. There are a couple of ways we can go about getting this. All right? But the first thing, let's make sure we understand what's going on here. And by the way, I look at this, I'll just tell you the, maybe I shouldn't tell you the answer yet. As I work you through this, one might think, oh, I just know this because like I have it memorized. But it's not that I have it memorized, it's because I understand where something's coming from. We talked about this in lab, I think last week or something, with one of the two labs, about I was always really bad with courses that required like memory work. If I had to memorize something, I couldn't do it, right? But if there was memory work that wasn't really like having trivia memorized, but you understood where something came from, like I'll never forget that thing I need to remember, if I understood where it came from. And let's make sure we're getting an understanding of why the answer is what it is in this particular example. But first, let's make sure we understand the core pattern that's happening here. We've got two loops. I starts at 0 and goes through n. That outside loop is going to run n times. But the trick is, how many times does that inside loop run? And what's interesting is, well, it changes for every time the outside loop runs. When I is 0, right? So it's the first time the outside loop is being run. How many times will that inside loop run? N. Okay, we're done. I is now 1. How many times does that inside loop run? N minus 1. It runs one less time. And the next time it'll run one less time, and one less time, and one less time, and one less time. So, if we go back to what I always love drawn out, the inside loop runs n times. We have to add up the total amount of work done. Plus n minus 1 times plus n minus 2 plus, plus plus 2 plus 1, right? The first time it's going to run n. The next time it's going to run 1 less. So it's n minus 1 total amount of work. Plus n minus 2 units of work. Plus n minus 3 units of work, and so on and so on and so on. I know we've looked at this before. What do we call this thing? Nope. You should feel terrible about yourselves. What do we call this? This is an arithmetic series, right? If you don't recognize it, just turn it around. It's 1 plus 2 plus 3 plus 4 plus da 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 da, right? And who remembers that little formula for arithmetic series? Oh, come on. Now I'm offended. Now I'm offended because it just goes back to what I was saying. If you think you need to memorize some function, like some formula, no. If you understand where the formula comes from, well, then it's fine. Think about it like this. How many things are here in total? How many terms are being added together? N, right? Right. So let's take this one. No, here, let's get a different color. Let's take this. No. I'll just draw. Take this one and add it to this one. What do you get? No, you get n plus 1. Let's write that down. N plus 1, right? Okay, great. What if you take this term and you add it to this term? What do you get? Oh, oh my God, it's another n plus 1. See, you get it. You're like, what? What happens if you took n minus 2 plus 3? What do you get? N plus 1. So we actually have a bunch of n plus 1s we have to add together. But how many do we actually have to add together? No, not n. N over 2. Why n over 2? Well, I took the first and the last thing, right? So I eliminated 2 from the total of n. So I don't have n things. I've got half of them because I'm taking 2 at a time. So that's just n plus 1 times n over 2. Now, to be clear, when we're talking arithmetic series, there's a more general form of the arithmetic series expression, but this is going to work for us here. So that's where it came from, right? So try not to forget what the arithmetic series is. That's just add the things together. Right? Don't you remember me telling you the story? It goes back to, is it Gauss? Check, it's Gauss? Okay, I knew it was one of them. And the story was, he was like a little shit in math class. And so the teacher gave him busy work, go add up all the numbers from 1 to 100. He came back in 2 seconds, was like, here. And they're like, how the hell did you do that? They're like, isn't it obvious? You just do that. I'm assuming that's an apocryphal story, but it's still interesting nonetheless. So there we go. And if you multiply all this out, what do you get? Well, you get n squared plus n divided by 2 look, when you look at that, if that's our t of n, what's the big O going to be? N squared. So we saw an n squared before, but this is obviously a little different because the n squared we saw before is I needed to do n things n times. But not anymore. I needed to do n things one time, and then n minus 1 things, and then n minus 2 things, and n minus 3. So it wasn't quite the same, but it will still grow like n squared. Even though we're actually doing less work every time that loop runs, it's still n squared. So that's one way to kind of like think about how to get the n squared from this particular example. Again, for everyone that's wondering why I'm pointing over there, it's because of the screen that I can see. But think of it this way. We could think of it another way. On average, how many times is the inside loop going to run? Well, we're talking loosely here. On average, how many times is that inside loop going to run? N over 2. Why? Well, the first time it ran n times, the last time it ran once. The second time it ran n minus 1 times, and the second last time it ran 2. So like on average, it ran half of n. So if I'm doing half of n things n times, it's n squared divided by 2, right? But it's still n squared. So that's an even easier way to kind of think about why it's n squared. Yeah?
So, care at all about, like, this is like the upper bound running way. Do we care at all about the average and the lower bound?
In general, yes. In 162, no. We're not going to worry about that. Because they get a little trickier. And often, this is the one we really, really, really care about. Another way to think about it is, like if I'm drawing this as a square, right? If I've got a square, right, and this square goes from n n, right? The first time through the loop, I'm going to just draw it as a straight line. I'm running all n things. But the next time through the loop, I'm doing a little less. And then a little less. And then a little less. And a little less. And a little less. But we all know triangles are just half of a square. So it's literally like, oh, it's half of a square, but it's half is just forgive the fact that that's not a great half of a square, right? Just go with me on it. But it's literally half of a square. I'm like, well, half of a square, half is a coefficient. It's a square. It's literally a square, right? It's like geometrically a square, n squared. There we go. It's quadratic. And remember, y to the power of 2 is quad. Quad means 4. 2 is, it's because it's a square. Squares have 4 sides, right? How many of you, and be honest, how many of you, when I said that the other day, about like it's quadratic because it's square, has 4 sides, how many of you were legitimately like, oh shit, that's why it's called that, right? See, there you go. And isn't it weird that no one like told you that, right? I remember when I found out, which was shockingly late in life, and I was like, well, it makes sense, but why did no one tell me? Exactly, it's cubed. So, but that would be like ninthing it, right? Instead of squared, you have, or no, 6 sides, right? 1, 2, 3, 4, yeah, 6 sides. Yeah.
But like if you think about it, you have it in
It's also why, like, you ever, universities, like, we don't really hear, but universities, you ever hear like of a part of a school called like the quad? Yeah, that usually means it's just some area that's like squared in. That's literally what it means. So, squares and 4, man. Same shit, I guess. Anyways, back to topics. So, this particular one, I would say, is n squared. T of n's more complex, but remember, we're lazy. We just want to know big O. It grows like n squared. And remember, it's not, When I talk about big O, I'm not saying this is the amount of work it takes. I'm saying the amount of work it takes changes like this as n gets bigger. That's what I'm saying. Okay, yeah. Now, here's the trickiest one for you. This one's tricky. I'll give you a few moments to think about this one. Yeah, I don't want to hear an answer. It's tricky until you know, and then you're like, oh, yeah, it's obvious. Obviously, the trick here is what's happening to I. In 1 year, back when I was teaching at Western, I had this as a question on an exam, but I stupidly started I at 0. And so when I was asked, what's the computational complexity, everyone kept giving me like the wrong answer, like it would run forever because 0 times 2 is still 0. And I kept getting all these weird answers, and I was like, why is everyone wrong on this? I feel like we covered it. And then finally someone showed me, I'm like, oh, okay. Raise your hand if you don't need to even be that confident, but if you have a guess in your head. Really high, I want to see, really high. Now, who is brave enough to tell me their guess? And you can't just tell me, you have to tell me why. Yeah. Root n. Interesting. I like where your head's going. You're wrong, but you're close. You've got the right idea. I don't want to pick you. I want to pick somebody else. I'll pick you. N to the power of 1 over 2. I feel like you're just about as wrong as they were. Yeah, I'd say. Yeah. Who else wants to guess? You had your hand up. What were you going to guess? You were going to say? Did anyone here not guess root n? What were you going to say? Log n. But why? Was it because it's the only obvious answer at this point? Kind of process of elimination?
Just because it was being squared, so each time, like it's like shrunk in half.
Yeah. So I'll explain this, and my hints are pretty good, but without a good starting place, it's kind of hard to go. Think about, so the question is, how many times will this loop run relative to the input size? And for anyone that was saying log n, you may have been wrong, but you had the right idea. Like it's definitely not linear. It's definitely like less than linear, right? Like it's like getting smushed somehow, right? By this like power of, by the fact that it's being doubled every time. So let's think about it like this. And I know this is also tricky because whenever you're thinking of a loop and it's growing, you're thinking of how fast something's growing. Like the number's going to go from 1 to 2 to 4 to 8, 16, 32, 64, etc. It's going to keep doubling, so it's growing. But the trick for me to understand this is to kind of flip it, is to say how quickly are we running out of like steps? How quickly am I moving towards the end? It's a loop. The loop has an end. N is a fixed, n is variable, but once it's set, right? If n is 1,000,000, that loop is bounded by 1,000,000. If n is 1,000,000,000, it's bounded by 1,000,000,000. So how quickly am I approaching that billion? That's kind of how I think about it. So if I go 1, 2, 4, 8, and so on, like I'm taking bigger and bigger steps. But to me, it might be helpful to go the other way. Let's say we had n as 1,024, just some arbitrary number. Entirely meaningless. 1,024. If that's the bound, right? And we were able to like step to 1,024, So we're at like the end of the loop. The loop started over there. I'm at the end of the loop, okay? And I'm 1024. Where was the previous step? At 512. Half of where it was, because you double 512, you get to 1024. So we got like halfway there, right? The last step actually was half of all of everything I needed to like go over, which was kind of neat. So if I'm here now, where do I go? Where would I have been before now? 256. And before there, 128, 64, 32, 16, 8, right? So if you think about it in reverse, we are actually eliminating half of all remaining elements at every step. We are eliminating. We are covering, we are jumping half of the remaining elements left. From 1024, I jumped to 512. I eliminated like half of those numbers. Then I halved it again, and I halved it again, and I halved it again, and I halved it again. So remember, you remember, like, okay, if I'm counting 5, if I'm adding 1 5 times, like if I'm counting 5 times, that's the same thing as like just plus 5, right?
How many times are you multiplying by 2?
Yeah. So remember all these basic mathematical operators, these arithmetic operators that you've been using since, I don't know, you were this big? They all like come from somewhere. And we could start with like the very simple math, and we could say like, okay, let's invent arithmetic right now. We start with one thing. We're allowed to count. You can count. All right? So if I'm at 5 and I say count from 5, so that's 5, 6, 7, 8, 9, 10, right? Like we can count. But with counting, like if I say like count 5, that's 5, that's just plus 5, right? Like counting, a generalization of counting is just addition, right? And then if I say, okay, great, we can do addition. So now take 5 and add 5 to it. Okay, that's 10. Okay, yeah, so we've got addition. But now if I say take some number and add 5, like take 5 times, well, that's 5 plus 5 plus 5 plus 5 plus 5, right? But then you just say, well, that's just addition. And of course, what's the opposite of addition? Or sorry, that's addition, that's multiplication. Oh. So what's the opposite of multiplication, though? The inverse, division, right? So whenever we get an operator, we can do the inverse operation. Just like what's the opposite of addition? Subtraction, right? So doing counting a bunch is just addition. Doing addition a bunch of times is just multiplication. But then, of course, what happens if I say do multiplication this many times? Well, that's just like an exponent, right? That's all that is. If I say take 5 times 5, like take 5 to the power of 5, right? Well, that's 5 times 5 times 5 times, right? It's just, that's all that means. But what's the inverse operation? Well, that's log. The inverse operation is log. So, long story short, if you keep doing divisions over and over and over and over and over again, well, that's a log. But you need to know the base of your log. And commonly in the math we use base 10. We're obsessed with 10. Humans love 10, I'm telling you, man. Yeah, we have 10 fingers. Why wouldn't you count in base 10? It makes perfect sense. Even though it's entirely arbitrary. Which that's an important thing to remember. Like, why do we count to 10? Why do we have 10 symbols, 0 through 9? I don't know, probably because we have 10 fingers. It's because it makes sense to you, but like it's entirely arbitrary. Right? Other people had different bases. The Syrians had like base 64 or something crazy. Oh, they were weird. But they're the reason, like, no, they had like base 60, right? And that's why, like, by the way,
Because like how like minute.
well, there's so many, like, it has so many like even divisors. It's actually, I was teasing, but it's actually goddamn genius. That like base 60 is brilliant. There's so many reasons it's nice. It's got so many factors and everything. But it's because of them, like there's 60 minutes in an hour, there's 60 seconds in a minute. Like literally because of them, that's why we have it. Anyways, you want to know why it's called a second?
Sure.
I know. It's because it's the second. You got minutes, and then the second one, well, seconds comes after minutes. Literally, that's why. Yeah, it's crazy. Yeah, I know, right? Isn't it cool? Computer science, man. You learn everything. So, long story short, we're talking about the base. If we're dividing by 2 every time, the base is 2. So I know you're thinking square root because you're thinking 2, and I can see the connection there. But it's actually log base 2. And commonly in computer science, we don't write the base 2. It's assumed to be base 2 unless otherwise specified.
We're just it's kind of,
We're halving it.
dividing the amount of work, like the distance from the end by 2 every time.
Yeah. Now, going back to the way the question was posed, I start at 1 and I'm doubling every time. That sounds, well, you're doubling every time. That's like an exponent. And you're right, but we have an end point. And we're going to be approaching that end point exponentially. So we are actually eliminating, like because we're approaching some endpoint, we're actually not really. We are rapidly moving towards an end very quickly. It depends how you look at it. If you're like, these operators sound really related, they literally are. It's the inverse of one another. Any questions about that? So this particular one would be big O of log base 2 of n. Raise your hand if you were like, yeah, that actually was my guess. 2 people. Well done. Well done. Raise your hand if you were like, okay, square root of n. Yeah. So your head was in the right place. You weren't correct, but you were like, but like the spirit of what you were trying to like get at was correct. Like it's clearly not n, it's like less than that. It's like, it's bounded because we're growing really quickly. So you're right for thinking that. You didn't get to the correct answer, but you were very close. So, now that we're equipped a little bit with thinking about this type of stuff, and to be clear, that particular example, that's a particularly like complex example. Right, like you don't see that often. Log base 2 you see often, but like an example with the loop like that, that's a little peculiar. But let's compare our linked stack to our array stack. How much work is popping and peaking from our linked stack? Constant time. Our linked stack, it's arbitrary size, and we pop from it. Well, that's just constant time. You update the thing at the beginning. It doesn't depend on how much stuff is in that linked structure. And here's the array stack example. How much work is there? It's still constant time, right? You just go get the thing at the end of the array and decrease the size, whatever. All of those things are just like 1 unit of work. You add it together. None of it actually depends on the size of the stack. The amount of work that these methods do not depend on the size of the stack. All right, so how about pushing? Here's your linked stack. How much work is the linked stack for a push? It's constant time. You just insert to the beginning of a structure. The amount you insert to the beginning of the link structure, the amount of work that's happening here does not depend on any size of that stack. Now, how about pushing to an array stack? So, how much work is this?
The lower bound is just constant, but the upper bound is
Yeah, I mean, you're right. Like, it's constant time unless we have to expand capacity. If we have to call expand capacity, how much work is expand capacity? N. You got to take all n things from my stack and copy them to another array. So it's linear. That actually depends on the size of the stack. So based on what you see here, which of the two implementations has like a better computational complexity? The link structure. To clarify, let me see if the push and the pop of the link structure were constant. The pop from an array structure is constant, but the push for the array structure might be linear, right? Because I might need to expand capacity. So what should you use? It depends.
If it's a stack, then yeah, because you're always, acting on the end of it, then it's kind of.
So the point I'm making here is just kind of like you're doing a good job at exercise or demonstrating it right now, is you have to think about this a little bit. You have to really rationalize and consider what it means. Now, to be clear, in this particular example, if I say, do you want the array or the linked implementation? There is a correct answer, a very correct answer. Everybody knows it. What is it? No, there's a very clear answer.
Link structure, if there's no like.
No, wrong. Always use the array. Arrays are way faster. Always. And then you're going to say, well, but it has that linear time thing. The linked one never had that. You're right. But when we're talking about how your computers work and how Java works and all the stuff that's going on under the hood, the array one is always going to be faster if you have a stopwatch. It's going to be. But this is where computer scientists try very careful to draw the difference between what the mathematics says, which is what we're doing now, coming up with the complexity analysis, and what actually happens in practice. And another interesting thing here, I would still say, computer scientists would still say your push on your array structure is still constant time. And you're going to say, yeah, but every once in a while you have to expand capacity. And that's
N times you have to do n things. So
exactly.
divide by n, so it's one.
So let's hit what you said and then we'll be done. Real quick. How many times, I have an array of size 50. How many times do I get constant time pushes before I have to do an expand capacity? 50. And then I have to do 50 units of work. Then I can do 50 more pushes because of the 100. So I can do what we call amortize that linear work, which means we just pretend that those n units of work we have to do, we spread out over the previous n pushes. So instead of each push taking constant time, it took 2 times constant, it's still constant time. So that's how we think about it. But that's not that important. Anyways, we'll see y'all later.